Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Uh, Today, now only four of you join the class. Are the other with you as well? You are with the other in one room or not yet? Okay, they are joining. All right, so let's start. Alhamdulillah. In this morning, we can continue our lesson about competitive programming. And glad to see you again in this moment. And we will continue discuss about bipartite matching. And before we start the discussion, let's be praying together. Allahumma inna nas'aluka nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Allahumma inna na'udzu bika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Rabbana zidna ilma warzuqna fahma. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. Okay, so let me share my screen. So in the past meeting, we already discussed about paper matching, and we have discussed about problem A, B, C, and E. And for problem A and B, it is just about bipartite, and there is no matching here, so we can solve them by GFS. And how about C? We already discussed it before. So minimum edge cover is equal to the number of node minus maximum matching, right? You remember about that? And the intuition is quite simple. So for example, given n nodes and then given m streets, and then we want to secure all the nodes by placing some card in the edge. So we can choose some edges. So when we place a card in an edge, so both of the node connected by this edge is secured. So what is the minimum number of card we can place? So one card. If one card can only secure one node, then the number of card is equal to n, right? Is equal to the number of node. But in fact, a card can secure two nodes, right? So we want to maximize a card that connect two nodes. Okay. So that's why if a card connect two nodes, it means there should be two nodes connected by an edge, and we want to make it as maximum as possible. And the nodes will be different, because if the node is same, so securing this is redundant. So it is just like this, only securing this node, and this card securing two nodes. All right, so the number of cards during two nodes is equal to the maximum matching. That's why we already secure 2m nodes. So the rest of node is n minus 2m. That's why the total card is equal to n minus m. Okay, so I haven't solved you the implementation before, but maybe one of you, Jawad Akbar, already solved it. The idea is same, right? Just find the bipartite matching and then just like the previous one, right? M plus n minus 2m. Okay, it is correct. Yes. Or you can also make it n minus n divided by 2, right? N minus m. Okay. And I have tried to implement as well using bipartite matching, right? So just input the graph and then just iterate for all nodes, right? For all nodes, if it is not paired yet, just try to DFS. If DFS is successful, so just add the answer by 1. And then the answer is n minus answer. Alright, it is quite simple. And the DFS is just like this. I hope you remember about how to implement bipartite matching. So if it is visited, so just return false. If not visited yet, just make it true. Alright, this is how to reset in O1, right? I have explained to you as well. And then just try to check for all neighbors, right? Just check for all neighbors. Is it available? If it is available, not connected yet, and py is equal to 0, so just connect them. Just connect them, x connect with y connect with x, and then return true. If it is already matched with the others, so just try to find the pair for its pair. So when x trying to take over y, so the pair of y should be find the other pair, right? Just try to DFS. If failed, so don't take over him. Don't take over it. But if this not success to get a new pair, so it is allowed to take over this. All right, that's the implementation of bipartite matching. Okay. Before we continue, is there any question? I think not yet. So let's continue to discuss problem D. So given a directed graph and we can remove an edge or add an edge, and we want to make the graph interesting. The target is to make the graph interesting by removing and adding a new edge. And we want to minimize the number of changes, so the number of removal and addition. All right. So what is the definition of interesting graph. So let's see some criteria here. The graph doesn't contain any multiple arcs, so there is no multiple edges right like this. But it is allowed to make multiple arcs but different direction. Okay, it is not allowed, but this is allowed. All right. What else? After that, there is a vertex V, and let's call it as a center or call her. Okay, let's call her the center. All right. So all other nodes. So there is an edge to and from other nodes, right? So the curve is like this. Even itself, so it must be a self loop here. Okay, is it understood? So it is just like star graph, right? And then what else? The out degree and in degree for all vertex except her is equal to 2. All right. So now what is the degree of this node? How do you think? What is the degree of this node? Yes, in degree is 1, out degree is 1. But we need to make the in degree is equal to 2 and the out degree is equal to 2. So we can make the other edges like this. Here, for example, like this, then like this. Okay. Now, is it correct? If we delete V, we will have bands of cycle. That's it. So if we remove V, the interesting graph should contain some cycles. Cycle can be with size 1 or 2 or 3 or any size. All right. Yes, that's a good observation. So let's check for the samples. Let me draw the graph. 1 connect with 1, 2 connect to 2, 3 to 1, 1 to 3, 3 to 2, 2 to 3, 3 to itself. Okay. Is it interesting? Yes, so no need to change anything. Just see out 0, right? How about this? Just like the previous one, right? But there is no 3 to 2. There is no this edge. So how to make it interesting? Just make this edge, right? So just see out 1. All right. What else? How about the last sample? Initially, the edge is only this. So how many edges we need? 1, 2, 3, 4, 5, 6. All right. So we need 6 edges, right? Is there any other ways to make it interesting? Yes, of course exists, right? So just make it like this. All right. Is it correct? Is this interesting? We need six edges as well. Okay. All right. So do you have any idea to solve this? So let's see the constraint. N is only 500. M is only 1,000. What does it mean? Okay, so the complexity of n square m is still accepted somehow. It's quite fast since bipartite matching can not too predictable. The complexity is not too predictable. Okay, let's just one of the vertex SP and see how many it. That's it. We will try for its vertex as the center. Okay, that's a good observation. And then see how many edges are needed. Then the deleted graph and see how many edges. Yes, that's it. That's the general idea. Okay, fix some v, satisfy the constraint of v and delete it now. Yes, that's it. So to have a permutation of graph. Yes. Okay, yes, that's correct. So just try for its nodes as a center. Of course, a center should be connected with 2n minus 1 edges, right? So just count the number of edges or current edges. So how many edges we need to add? All right, that's the cost to make it a center. And then just remove it. After that, the rest of nodes may be already connected by some edges, right? So how to check them? How to find the minimum operation so that they become some cycles? All right. First, we have to remove all multiple edges. Then, okay, remove multiple edges. Which one we need to remove? For example, for these multiple edges, we want to remove to the right or to the left, or both of them. First, we need to remove, right? Because we cannot keep. I think we can keep them as well, right? Okay, wait. Do you mean multiple edges in one direction? So it is guaranteed that initially doesn't contain any multiple edges. Okay. If there is okay, yes. All right, yes. That's when there are some multiple edges, then we need to remove them. But fortunately, the constraint is quite friendly, so it doesn't contain multiple arcs. Okay, what else? We already got this observation, so now the rest of the problem is just how to minimize the number of operation to make them become some cycles, become interesting. So become cycles like that. Even self loop is a cycle. Like this is also a cycle. Okay. So the number of operation is equal to addition plus removal, right? The number of addition plus the number of removal. Yes, this yes. And then you know the the current number plus sorry, yes. The current number or sorry, current edges is equal to or the resulting edges. Or let's create uh, two sets. This is the initial edges and then this is the final edges. So we need to remove this and we need to add this, right? So in order to wait, the final edges, how many number of edges here? Do you know how many number of final edges? Because okay, yes. Or let's remove the center. Let's forget about the center. So just n, right? Okay, the final edges always n. And how about the initial one? The initial one already fixed, right? Okay, it is already fixed or constant. So it means if we want to minimize operation, minimize addition and removal, so we want to maximize the intersecting, right? The persistent edges that is persist in the initial and final. All right. So it means we want to maximize using the current edges. All right. So we want to use the current edges as maximum as possible. All right. So for example, there is a graph like this. For example, then we can use this and use this and use this and then use this, for example. Okay, so just add this, right? Or use this and we and just add this. All right. We want to use as much as possible. So what does it means? We can create a graph. Let's make an indexing here. So we can create a bipartite graph with 5 nodes, for example. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And just create an edge based on the edge here. 2 can go to 1, 1 can go to 3, 3 can go to 2, 1 can go to 4, 3 can go to 4, 2 can go to 4, 5 can go to 4, 5 can go to 5 itself. All right. Do you know? One node can only pointing one another node, right? And one another node also only can be pointed by one another node, right? So it means here just like creating maximum matching here. Is it correct? Okay. So the answer is equal to the maximum matching here. Sorry, not the answer. The maximum intersect between these two sets is equal to the maximum matching here. Why? Because after we creating this graph, so if we want to make it, we want to use this. Okay, wait. How the bipartite graph is created? The bipartite graph created based on this. So if there are 5 nodes, so we want to create 5 out node and 5 in node. So if, or let's say this is from, this is 2. So if there is an edge from 2 to 1, so just create an edge from 2 to 1. If there is a self loop from 5 to 5, so just create an edge from 5 to 5. Okay. All right. So, you know, because the interesting graph is when the in degree is 1 and out degree is 1, so it means it is only can match with 1. This is also only can match with 1. So if we want to maximize the number of useful edges, so it is just like we want to find the maximum matching here. All right. Okay. So it is correct, right? Is there any other question? Okay. So just find the number of such node, right? The number of maximum matching. So if the number of matching is m, so the additional edge equal to n minus m, right? And then the removed edge is equal to what? Wait, m is already exists, so let's make it x. Okay, this is n min x, n minus x. All right. And then we already checked the degree of phi, right? The degree of phi, yes, that's it. Because we already removed the number of degree like this. So the initial edge is m minus degree, right? M minus degree minus x. Yes, that's it. And then we also need to add to n minus 1 minus the degree of the center, right? Okay, so just add this by removal and addition. Plus m minus d minus x. And then plus n minus x. All right, so the result is 3n plus m minus 2 times degree minus 2x minus 1. Okay, this is the result. And just find the minimum one. Okay. T is the degree of the center, x is the maximum matching. The time complexity is n times the complexity of bipartite matching. Actually, the worst case is around n times m, right? So n squared times m. But sometimes it is faster than the worst case. It is usually faster than worst case. So if n is 500, m is 1000. So the worst case is 25 E7, around 2.5 E8. But sometimes it is multiple times faster. Okay. Is there any question here? Or we can make it faster by creating grid matching, right? So before we do the optimal matching here, just iterate from 1 to n, and then just grid matching. The complexity of grid matching is just OM, right? And somehow it is so much faster. All right. Is there any other question? Should I show you the implementation, or you want to try by yourself? I think bipartite matching quite new, maybe new for us. So we need to see some example of the implementation. All right. Let me copy from my previous implementation. Okay, so for this node, sorry, for this problem, given n and m, yes, and then input the number of edges like this. The edge is directed, but we need to store the number of in degree and out degree, or just degree. All right. After that, just try for a center. Let's create a variable c, which is equal to the center, starting from 1 until n. And then let answer is equal to 0. And then just find the matching, right? Just find the matching. So initially this initially all of the node is not matched. And then just try to TFS like this, right? Okay. After that, I think it is not the answer. Let's make it X. So the answer is okay. Just create the formula before. And then we want to do TFS, right? We want to find the pair. But if y is equal to the center, just skip it. Don't go to the center. Okay, so here we also skip the center. If I equal to C, then just continue. C means continue, right? And then what else? Want to find TFS like this. And then just do this. Okay. All right. Okay, 3n plus m minus 2t. Yes, that's correct. Plus m. Where is m? I think we need to add m here. Is it needed? And m minus 2t minus 2x minus 1. Whether this vertex is in out. Okay. Yes. So we always So the parameter is always out. It's always out. It's and we always no need to do that. So let's try to input the samples. Wait, okay. I think we need to store my here. Wait, -1. Let's check the X here. One, two, 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 three, two. Always two, right? But let's check the the graph is like this, if I remember correctly. So when we try to remove this, okay, we can connect this, connect this. This is perfect. How about this? We connect this and connect this. Always two, right? But how about the degree? Okay, the formula is 3n 9 plus m is equal to 7 minus 2gc if c is equal to 5. Well, okay, I think because it is computed twice, so it is 2n, no need to minus it with 1. All right, so the degree counted twice for this self loop. All right, let's input the other one. After that, I want to explain how to differentiate between the left part and the right part. And this is 1. And how about this? This is 6. All right. So what does it means? So for example, there are two groups, right? But groups is size n. And actually we can differentiate the size. It is also okay. Then array B means what is the pair of the right nodes? Okay. If it is already matched, so it is pointing the left group. But if it is equal to 0 means it is not paired yet. But for TFS, it is for the left group. This is the right group. This is left group. This is the left group. Okay. So if it is visited, just return false and then just make it visited. And then Y means always right group, right? Because L is left group. If equal to C, then just continue. Okay, we always exclude C, right? And then just check whether the right node is available or not. If not available, so just sorry, if it is available equal to 0, so just pair X with Y, right? So py is equal to x. Just written true. Then what if it is already matched with the other? So if we want to take over, for example, this is x, this is y. It means we want to DFS by, right? So again, the parameter is for this node, right? So don't worry about the left group and the right group. It is easier to implement the GFS. Okay, is it understood? All right, so this is how to implement the graph when the left part and the right part is already fixed. If the left part and the right part is not fixed yet, then we have to check first whether it is already paired or not. If already paired, just skip it. And then we also need to make this two directional, right? But for this case, just make it one directional. All right. And yes, the worst case for the final answer is equal to n squared divided by 2, maybe. Yes, maybe we can make it like this. Okay. All right. I think we just need 500 for this. Okay, let's try to submit it. Okay. So I think we have already discussed about problem E, right? No need to do DFS. For this problem, we can just greedily matching them. So just count the number of XL, number of SM, and so on. And then just greedy from S. Please, for all person that only accept S, just connect it with S. After that, for all node only connected with S and M, please prefer to use S. But if S is empty, so just use M and so on. Okay. Is there any question for this problem? Okay. So let's continue to problem F. If you read this, so the problem is like this. Given some exam, sorry, yes, given some exam, and one exam is held on 2 days. in day AI and day BI. So we can choose whether do that in day AI or BI. But in one day, we can only pass one exam, right? Cannot pass more than one exam in the same day. All right. So if there are M exam, and for example, this exam can be done in 2 days, and this is also done in 2 days, and so on. So it is just like matching, right? Because in one day only can solve one exam, and one exam just need to solve one in one of the 2 days. Right. Yes, that's it. That's the brief explanation of the problem. So the question is, we want to pass all of the exam as soon as possible. So just find the minimum day, minimum index of day. So in that day, we already pass all of the exam. Or print minus one is if we cannot do that. So is there any observation about this? For example, for this case, in the first day, don't do this, because if we do this, we need to do the second exam in seventh day. But please do this and then just finish the second one in the fifth day. After that, for this case, just do this in fifth day. So we need to do this in the first day and then do this in the seventh day, because we want to avoid 13, right? If we do 5 here, so we need to use this. What else? How about this? If we avoid 80, so we cannot do that, right? If we do this in 10 day, this in the 40 day, we cannot do the rest. So we always use this. All right, so the answer is 80. How about this? We just can do two of them, right? We cannot do the other three or the other one. So just output minus one. All right. Do you have any idea to solve this? Can can add h from we can binary search on the next day. Yes, the binary search observation is correct. So if we can finish before day I or day mid, we always can finish it before day mid plus one. But if in midday we cannot finish them, so it means in mid minus one we also cannot finish them. We can add edges between A and B. Then we will eliminate vertex cover. All right. I think it is not vertex cover. We mean matching, perfect matching, I think. Vertex cover means we can choose some vertex, so all edges is covered. All edges is connect to at least one chosen node. So if the graph is like this, then the vertex cover is just one, for example. Okay, just made it. If a day is being asked by only one exam, yes, that's a good observation. Because we do binary search, right? We want to restrict the number of day. So we already fix the number of day. So for example, when mid is equal to 50, so it means we cannot visit this, right? Cannot do in this day. So we always do this. Okay. So it is correct. We just like want to find the maximum or perfect matching, but the constraint is so big. So can we optimize it? N is up to 1,000,000. So if we can solve it in ON or can check it in ON because we need binary search, so the complexity become n log n. Okay. So we are allowed to check in ON, right? So just check one by one. If one of the day is more than mid, so just choose this. If both of them more than mid, so just return false, right? It means there is no, there is, it is impossible to solve them to pass all of the exam. Okay. After that, when we already fix some value, so just insert it to a set, right? Just insert it to a set. If same value inserted twice, so just return false, right? So make sure the day is different. Okay. After that, what if both days is less than or equal to mid? It means we can choose one of them, right? Between 10 or 40. Now please forget about bipartite graph for a while. We just want to create any graph. Just connect between 10 and 40. And then for example, we want to connect 40 with 80 and 80 with 10. All right. If some value already exists in the set, so it means it is removed, right? Okay. All right. So after that, we want to choose one node, right? For each edge. For example, this edge, choosing this node, this it's choosing this node, this edge choosing this node, right? Okay, so both of them is got a J, so it is allowed. So if there is a cycle, so it means always allowed. And what if there is no cycle? Is it allowed as well? Yes, okay. If some exam have a degree 0, yes, return false. Yes, that's it. That's correct. So if the graph like this, for example, so just remove the leaf, right? If there is a J that only connect with one, just remove it and then remove it, remove it. So the rest is just cycle, right? If the rest is just cycle, so we can do that as long as there is no multiple edges, right? But if there is multiple edges like this, so we cannot do that, right? What if the graph is like this? Is it allowed? Okay. I mean, let me create you a bipartite one. This is the exam, this is the day. This is connected with this and this. This is connected with this and this. This is connected with, wait, okay, yes. Let me create 4 8s. And then let me create another edge connecting this and this. Okay, can we solve this? Degree of the exam are 2, right? Okay, yes, we cannot do that because the number of exam is more than this. That's it. Okay, as long as the number of exam is less than or equal to days, because we already remove all the node that the degree is 1, so it is always come cycle, right? So it is always equal, right? Exam equal to day. When exam is more than day, so just return false. And then if exam less than day means there is a day that only pointed by one exam, right? So remove it until there is no such nodes. So exam always less than, always greater than or equal to day. If equal then true, if greater then false. Okay, is it understood? I think I have solved it 6 years ago, but maybe the implementation is so different. So if there is no question, let's continue to problem G. Have you read this problem? Maybe Jawad people already read this. So the problem is functional, just like in IOI style. So given n and also vector of string. Vector of string is just like a grid, right? Grid of character. And then the constraint is up to 300. All right. So given a grid with n rows and n columns, and then we want to go from 1.1, want to go to n.n. And then actually we can only go to the right or bottom, right or down. But when we are in white cell, so actually the grid is represented by some character, either asterisk or dot. Dot means white, asterisk means black. If we are in black cell, so we can go to the right or to the bottom. But if we are in the white cell, we can go to the bottom or to the right or to the left. Sorry, to the right or down. So we always can go to the right or down. But for this, we only can move when we are in white cell. Okay. After that, the question is how many number of steps? For example, for this case, we just can do in 2 steps, right? So just return 2. Okay. And before going to the bottom right cell, we can modify the grid. We can modify the grid by swapping the column or swapping the rows. And we cannot, we can do this many operation as we want. So there is no restriction about the swapping like this. Okay. Is it understood? Okay. So do you have any idea how to solve this? Yes, that's it. So one of the observation is when all of them are black, so we need to move to n minus 2, right? Or just 2 times n minus 1. Okay. So we want to visit as many white as possible, right? So we want to visit as many white as possible. So we can skip some steps. After that, just go in normal way. So the result is 2 times n minus 1 or 2 times 2n minus 2 minus the number of white cells. Wait, this is also skip. Okay, all right. And then how to maximize the number of white cells? How do you think? Okay, do you know how to find the maximum number of white cells? So if there is a white cell, we can move it to the top left, right? So we can swap this here. Yes, that's it. Because we swap it here and then swap this row here. So if there's another white here or here, we cannot use this again, right? Because it become around here. So because when we do a step to bottom right, it means we skip that column, right? And also that row. So it means we also can pass another white in the same row. Okay. So it means in one row at most one, in one column at most one. So how do you think? Do you have any other idea? What next? What is next? Yes, that's it. We can find the maximum matching here. So just create a bipartite graph consisting of n nodes representing the rows and the columns. And then when there is a white cell in x point y, just make an edge. And in one row we can only choose one, right? So only match one and also column, and we want to find the maximum matching here. Okay, so after got the maximum matching, just use that formula. Wait, this is 2. So is there any other corner case? Do you see any corner case? Is formula always correct or not? What if m is equal to 0? Sorry, this is 2. If m is equal to 0, just do this, right? It means there is no white cell. Yes, that's it. So the corner case is when m is equal to n, right? Why? Because if m is equal to n, we can create a trigonal. But the last one is not counted because when we already finish in the last cell, we don't want to move again, so it is redundant. So just minus it with n minus 1. So when m is equal to n, the answer is not to n minus, sorry, is not equal to n minus 2, but n minus 1. All right. Okay, is there any other question? I think it is enough and quite simple. And no need to no need to differentiate the index. No need to make the column is n plus 1 until to n. No need to do that. Just keep it 1 to n and just use this idea. It is easier. All right. And then let's move to problem 8. Okay. If you read this, so all right. Even in jobs, each jobs has starting hour and ending hour, and skill level. And maybe there are so many jobs. And both of them is, or maybe we can say it, A is inclusive and B is exclusive. So we can immediately do this. So when B is equal to another A, we can do both of them. Okay. But there is another restriction other than just time. A person can finish another job if the skill level, the difference of the skill level is at most x. So for example, x is equal to 2. At the first time, we can do any job. We can do any job, for example, a job with skill level 7. So after that, we can do a job with skill level 5, for example, and then skill 6, and then skill 8, and then skill 6 again, for example. But from this, we cannot do a job with skill level 3 directly, okay? But we need to do another job with skill level 4, for example, or 5. After that, we can do this. Okay. Is it understood? All right. Then we want to hire we want to hire as minimum as possible. Sorry, not as minimum as possible. We want to hire M person, or just let's say there are M person or M employees that can do any number of jobs with this constraint, right? Time constraint and also skill level constraint. And x is not fixed yet, but we want to find the minimum value of x such that we can do every job by hiring employees. Okay, is it understood? All right. Then is there any idea? By research on x, that's it. We can do by research on x instead of finding x directly. Okay. So after x is fixed, then what shall we do? Okay, that's it. Then we have directed acyclic graph, right? Because the time always, okay, times always pass and never go back to the past. Okay, so there never a cycle. There's never a cycle because the time is fixed. After this node, we can go to another node like that. And but for different x, the graph can be different, right? So for example, the different the difference between the skill level is 5. So if x is greater than or equal to 5, the edge is exists. But if less than 5, the edge is doesn't exist. Then do you know when there is a directed acyclic graph, how to find the minimum path cover? Minimum path cover means how many number of path can intersect. Wait, path can intersect or not? Each job can be done by Atmos when support. Okay, Atmos when, so cannot intersect, sorry. So the path cannot intersect, and we want to visit all edges. Wait, all edges or all nodes? I think for path cover, it is connecting edges, but for this this problem connecting edges. All right. Yes. And then let's say we want to find the minimum number of subordinate, right? Minimum number of path. If the minimum number of path is less than m, so it means it is correct. Okay, yes. Even if they intersect, we can remove that job. I think not like that, because sometimes the node can, from this can do this, but through this node only. We cannot do directly from this to this, right? Because, for example, the skill level is 1, 1, 2, and this is 3, 3. And X is just 1. Okay. So we can only pass it once. So the number of vertex, sorry, the number of path cover is equal to 3. Okay. So if the minimum path cover is less than or equal to m, then it is correct. But if more than m, it is incorrect. So how to find the minimum path cover? So we need to create a bipartite graph, its size equal to the number of job, so equal to n. And this is the out node, and this is the in node. So if there is an edge between out and in, just create an edge. Okay. All right. Do you know how to create this graph? Do you understand the rule? Okay. Then just find the maximum matching as usual. Then you know the minimum path cover is equal to what? Wait. Let me see. Why not 4 and minus maximum matching? Wait, let me check the intuition. If we can match this, I think it is dialectical cyclic graph, so never never go up. Go up means go back to the previous job when we sort them by, yes, go back in time. If we sort them by, what can we say? Yes, just starting time. You can sort by starting time. Okay. The maximum matching means we can, okay, yes, that's it. Just n minus the number of nodes minus the maximum matching. Why? Because if we don't use any edge, So it means we need n path, right? Just create n path consisting of one node, right? Okay, you got it. All right, but we can use a path, right? If we use a path, then the number of, sorry, if we use an edge, then the number of path is reduced by one. If we take another edge, just reduced by one. If we take another edge, reduced by one. Is it correct? If it, okay. But because this is path, so the maximum out degree is at most one, and the maximum in degree is at most one. We cannot do this, right? We cannot do a branch because this is a path, and we cannot make like this as well because a tube at can only eat it at most once. All right, now it is makes sense, right? The formula is like this because out degree is maximum one, in degree is maximum one, and we can use these edges. All right, so this is how to find the minimum path cover. If the minimum path cover is less than or equal to m, then it is valid, but if greater than m, it is invalid. Okay, then what is the complexity? Complexity is at first block S. Interesting. The constraint is like this. Okay, so block S is around 30, right? And then, you know, the graph can be perfect DAG, right? Perfect directed acyclic graph. So the number of edges can be n squared divided by 2. Okay, so around this, right? And then multiply by the number of nodes, right? So the complexity is like this. So I think it is still okay. Okay, 1 or 10 to the power of 8, but divide by 2, and sometimes it is much faster. Okay, even if the SU matching is, yes, no problem. All right, so I think it is clear. Is there any other question? All right, and the time limit is half second. Okay, but don't worry, we can optimize it using the greedy matching before that. Okay, then let's move to the last problem. If you read this, I don't know, we can solve this or not. Maybe you can try to submit because this problem should be submitted in to source code, right? Do you know about this type of problem? So the type of problem are batch, interactive, and also output only, and also communicative. Do you know about this one? Not yet. Okay. So for output only, we will submit .zip, right? For this .c++, this is .c++ as well. But for communicative, we need to submit two or even more than two file. Yes, encoder and decoder. All right, encoder and decoder. Okay, so maybe you already do that kind of problem. Okay, so this is one of the one of this type. So we need to submit encoder program. Okay, yes, maybe just like APU 20 and 24. And some IOI problem is the type like this. All right. So let's see. I don't know. Can we submit it to widgets or not? If you cannot, so let me give you the link to the source. I have solved it before, so I can try to submit it. Yes. There are two code. How to submit it to the widgets. It failed. Okay, so we cannot submit here. This thing. Okay. Maybe. Or okay, please just submit it here. Right, so it is easier. So you can submit it here. So the problem is like this. There are n cards numbered from 1 to n. And then a spectator want to choose k distinct cards. Okay, so there are three parties, the spectator and then the encoder and decoder. So the spectator can give k cards to the encoder, and then the encoder can give k minus card by removing one card, and then T will give back that k cards. All right. Okay. And when E give to D, it is always sorted or just randomly shuffled. So D cannot know the order of card he will send. He already sent. Okay. So the rule is quite simple. Given K card for E and then just return K minus 1 card and then the returning card given to T and then T should return the K. Actually, there is a creator, right? Creator will get K minus 1 and then just sort them and then give to T. Okay. Wait, K plus 1? K plus 1. Okay, yes. Not minus 1, so plus 1. Okay, add 1 more. So yes, K plus 1, not minus 1. By adding 1 new card. Okay, so just return an integer, right? Just add 1 card and then for this also just return a factor. Okay. Okay, do you have any idea? What is the strategy for the encoder and decoder? Okay. For example, like this, the spectator choose card 2 and 5. So wait, not like that. Given 1 and 2 to the assistant, and then the assistant give another new card. Okay, and then just return, just remove that new card and then return the original card. The card is indexed by 1 until n, right? For example, given card 1 to 5, and then we add 4. So the encoder will add 4. So it means the decoder should remove 4. Don't remove the other. Don't remove 5, don't remove 3, don't remove 1, but remove 4 as well, because this is the number that we already add. But unfortunately, the encoder and decoder cannot communicate, right? So if they can communicate, so it is so easy, because assistant or the encoder can talk to the decoder that the added value is 4. So the decoder can just remove 4. Okay. Is the problem understood? Okay. So do you have any idea? What if k is equal to 1? Is there any idea when k is equal to 1? It means given one card and then just add another card and then just return that one card. Then what shall we do? And the value of n at most only 12. Okay. Yes, we can return with any label. For example, given 1 and then just add 7. Okay, and then the decoder will remove 7. Okay. Yes, that's correct. So for the second subtask, we can just add the value added by 1, right? So for example, the given card is x. So just add x plus 1 modulo n, right? Or x modulo n plus 1. Okay. So if x is 3, just add 4. If x is 7, just add 8. If x is equal to n, so n plus 1 is not exist, right? So just add 1. So it is easy to remove. Just remove the bigger one. But if the bigger one is n, so it means remove 1. Sorry. If the distance is not the distance is not 1. The difference is not 1, so just remove 1. The label should be less than or equal to 2. Yes, because the card is only 1 until n. And we cannot add the same labels, right? For example, even 1, 3, 5. We cannot add 3 because 3 already exists here. Okay. And we cannot add more than n, or cannot add negative value or 0 value. Okay. Is there any other question? Then how about subtask 1? What do you think? Card n never appear. So how to solve that? Just add n. That's it. Just add n and always remove n. Because we know n is never exists as the given cards. Alright, so we got subtask 1 and 2. How about subtask 3? If n is at most 6, so k is at most what? What is the maximum k? 2, that's it. Okay, if k is equal to 1, just do this. What if k is equal to 2? So the card is 1, 2, 3, 4, 5, 6. And then, for example, given 2 card, then which card we need to add? Okay. Is there any idea? We can solve it manually, right? So just write some possible values. And we also need to consider when n is equal to 5, right? If n is equal 4 or less than that, so it means k equal to 1, right? So don't worry, we can solve it by this. But if equal to 5, then just try this one. Okay. Just try for all possible three number, right? 1 to 3, 1 to 4, 1 to 5. And then 1, 3, 4, 1, 3, 5, 1, 4, 5. And then 2, 3, 4, 2, 3, 5. And then 2, 4, 5. And then 3, 4, 5, right? We can create a matching here, right? For example, 1, 2, add 3 here. If 1, 3, just add 5, for example. 1, 4, just add 2. 1, 5, just add 2. 2, 3, just add 4. 2, 4, just add 5. 2, 5, just add 3. 3, 5, just add 1. 3, sorry, 3, 4, just add 1. 3, 5, just add what? 4, 5, just add this. We cannot connect with this, right? 3, 5 can connect with this. So just take over this, right? 2, 5 can connect with this, for example. So 1, 5 can connect with this. Okay, we got a perfect matching, right? So can we solve this by doing this? Okay, sorry, I think times is up. So I think you get the clue how to solve this using bipartite matching, right? So I think that's all for our discussion today. Let's continue in the next meeting. Let's close our meeting with praying kafaratul majlis. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Assalamualaikum warahmatullahi wabarakatuh.